So I'm at the point where the X-axis servo is tuned, and I'll start on the Y here shortly, but I wanted to document the process really quick and how I got to where it is now. So what I did was I wrote a small G-code program that will oscillate the axis of my choice, and with that feedback I can get data from the servo into the JMC tuning software version 2.1.4. It has an oscilloscope where I can isolate the position following error, and I can adjust the scale of the graph based on how big that error is. So we'll run the Y-axis program and we'll see how bad the following error is with the stock settings. Okay, the program is running. That's all it's doing, is moving the axis back and forth. I'll start the oscilloscope. Let's take a look. Getting about 400 steps of error in each direction, positive and negative. Not that good. I think we can tune that out. I got much better on the X-axis. So we'll see what that translates to. Okay, so 400 steps of error. What does that equate to? In this servo setup, I have it at 4,000 steps per rev. Let's say 10 millimeter pitch ball screw, 12 millimeter diameter. So that 400 steps gives us 10 millimeter thread. Divide that by, or 4,000 steps, sorry. 2.5 thousandths of a millimeter of travel per step. Let's convert that to inches. Divide that by 25.4. And then we had 400 steps, so we'll multiply that, 400. And that gives us 1 millimeter of error. Ironically, everything's are 10s and 4s, so it works out 0.03937. We will get that much closer. I'm collecting information through this USB to RS-232 adapter, and then a DB9 plug breakout board that talks to the servo connection. I've connected JMC debug software to the X-axis motor, and we're talking to it. And now I can compare by retrieving all the parameters from the motor. I can use this parameter comparison tool in the software, loaded the factory settings, run the analysis, and it gives me the parameter values that have been adjusted. You can see there I have disabled the real-time automatic adjustment mode. That is the auto tune feature. The position control, gain 1 and 2. Gain 1 is static, gain 2 is dynamic, and you see everything else and the original values. The left column is what the motor is now. The right column is the OEM settings. Let's go ahead and run the X-axis oscillation program, and then we'll pull up the data on the oscilloscope in the software and track the following error on a tuned axis. Start the oscilloscope. It's recording. There are some waves there. Let's see if we can do any better by adjusting the scale. Each step here is 200 steps, or each horizontal line, sorry. So I'm going to reduce that to 20. Now we're starting to see what the error is doing. Still rather small. Move that to 2 steps per line. And now we really start to see the information. Okay, so the program finished. I'll run it again. But it looks like we're maxing at about 4 steps of error. Right at the start, we got about 7. through the program running at max rapid rate, which is at 300 on this machine, 300 inch per minute. I'm getting 4 steps of error. Let's translate that again. So if we remember, on the y-axis that was not tuned, 1 millimeter of error, 39 thousandths of an inch. Let's see, now we're running 4. So we've got 10 millimeters per revolution and 4,000 steps. Divide that by 25.4, convert it into inches. And now we're at 4 steps. So we're at about 3-4 tenths of a thousandth, theoretical. I say that because in a perfect world and the machine was absolutely rigid, that's what you would get. But we don't live in a perfect world, and this is not perfectly rigid. But you can see much better precision.